Okay. So, here is a summary of another multiplexing standard, which is basically asynchronous. That means, there will be provision for pulse stuffing once again, so that the individual clock at various multiplexing points need not be synchronized, and there may be little bit of shift in the frequency, and that will be taken care of through pulse stuffing. And this standard is known as IIT PCM Tdm scheme. So, it should be obvious that this scheme is as per the ITU-T, okay, International Telecommunication Union, and this is used in several countries, most all European countries and many other countries including India, okay, where the frame duration is the same as it was in T1 multiplexing scheme of 125 microsecond, fundamentally so because the speech signal bandwidth is always limited between 300 and 3.4 kilohertz. Let us sample at 8 kilosamples per second, and then the time frame here also, the frame which is of duration 125 microsecond is divided into 32 equal time slots. Earlier it was the time slot was divided in 24, isn't it, as per the T1 scheme, with 1 bit added at the beginning, okay, frame sync bit. But here the whole frame is divided in 32 equal time slots, and the overall rate of transmission is 2.048 megabits per second. 2.048 megabits per second in comparison to 1.544 megabits per second. Okay. Then time slot 0, there is a first time slot, is used for frame alignment pattern and for alarm channels. Okay. This alarm mainly indicates some kind of system monitoring alarm really. If the system is not working properly, some information has to be sent, it is for that purpose. And slot number 17, that means the middle slot. If you imagine slot 0 to 32, the first slot is allocated permanently for frame alignment pattern and for an alarm channel. Frame alignment pattern is something analogous to frame synchronization pattern. In the earlier scheme, the idea was to put 1 bit in a frame, and thus over a 12 frame period, a sequence of 12 bit would be sent, and that sequence would be used for frame synchronization. Okay, here it is somewhat different. Here one particular time slot is allocated, and that time the first time slot, and that is used partially for this issue of frame alignment or frame synchronization. Then time slot 17, the middle slot, is used for common signaling channel. So there is one time slot allocated for signaling purposes of all the 32 users. So, sorry, all 30 voice users. So, if you leave out slot number 0 and slot number 17, you will have 30 voice slots, time slots. So, 30 users signal will be multiplexed together, and all their signaling requirement will be catered to through this slot number 17. Because all user signaling will go through one common arrangement, we say it is a common channel signaling or common signaling channel, CSC, common signaling channel. So, by calculation one can find that the signaling for all voice users, for individual voice user through this common signaling channel will be at the rate of 500 bits per second per channel. So, individual user, as if his signaling requirements will be catered to at a bit rate of 500 bits per second. How much was it in the earlier scheme? No, that's 1333, double of that. Yeah, roughly 1.3 kilobits per second. So, here signaling rate is lower, we can see, okay, but ultimately this is also sufficient. So, this scheme is used extensively, and this is a summary of the first level of multiplexing, which is denoted by E1, okay, and somewhat similar to the earlier hierarchy, like from T1 we had T2, then T3 and T4. Here also we have a provision for E2, E3 and E4. So, here again is a summary only in terms of the overall bit rates. Okay. So, to keep conformity, we can define E0 or E0 as a basic signal of 64 kilobits per second from an individual user. Okay. So, individual users data is available at 64 kilobits per second. We may call this at E0 level of signal. And then the next one, as I mentioned, is E1, where 30 such channels from 30 voice users, they multiplexed, and the overall bit rate is 2.048 megabits per second. And the next level of multiplexing, 4 such E1 signals, they are multiplexed together, and we get E2 level of signal, and the overall bit rate now becomes 8.45 megabits per second. You may note that simple multiplication of 2.048 with 4 will not result in this. This value is somewhat higher, because at this stage, because ultimately this is an asynchronous multiplexing hierarchy, there is a provision for pulse stuffing. Okay,
How many bits?
you can calculate from here. Okay, sorry. Then at the next level of multiplexing at E3, we multiplex 16 E1s or equivalently 4 E2s to get this overall bit rate of 34 megabits per second. The next level is also defined at E4 at 144 megabits per second, okay, equivalent to 64 E1 signals, or 16 E2, or 4 E3s. Okay. So this E0 is a basic data rate from one voice user, and that is 8 bits per sample PCM, okay, resulting in 64 kilobits per second. Okay. So E0 I could have written here at the top to start with. As if we were multiplexing 30 E0 channels together, okay, resulting in E1 format at 2.048 megabits per second. So the multiplexing schemes that I discussed so far, they started from individual users. Now, if you go higher up and think beyond, especially with the advent of very high speed digital networks like optical fiber networks, etc., which offers a much larger bandwidth and hence a capability of transmission at the rate of several gigabits per second. Okay, the present technology perhaps allows few tens of gigabits per second. Okay, so in view of such a large capacity, bit transmission capability, beyond this value of a few hundreds of megabits per second, okay, 270 or 144 megabits per second, a few other levels have also been defined. Okay, and as keeping in view the corresponding technology, the way it is being deployed for optical communications and certain other high bandwidth wireless communication systems also, the multiplexing hierarchy has been extended of late in last 15-20 years, and there has been a different kind of hierarchy definition which are broadly known as synchronous hierarchies, meaning thereby that no more any lack of synchronism in the timing generator or clock generator is allowed. Okay, and everything must be synchronous, and as if there will be a master clock which will uh, which will send the clock signal, so that all the signals from individual sources will come at that same clock plate. So they will already be aligned, so there is no need for any pulse stuffing, etc. There are several reasons why it had to be like that really, and anyway, so this, and out of these synchronous hierarchies, these two are very popular. One is known as Sonet, synchronous optical network. Okay, actually it is a multiplexing format really, used specifically for optical networking, the way it was at least earlier suggested. And this was suggested by ANSI. ANSI, we know ANSI is American National Standard Institute. Okay, so it was deployed mainly in the US, Canada, and a few other countries like Korea, Taiwan, Hong Kong. Okay, while this was proposed and developed really in the late 80s and early 90s, ITU again came up. Okay, and it, because if you really follow the subsequent description of the Sonet and Sdh multiplexing format and the earlier description of T1 and D1 and spend some thoughts over that, you will feel that as if there are two parallel standards always existing in the asynchronous hierarchy as well as in the synchronous hierarchy. Okay, and whenever a standard is proposed sometime later, the standard tries to see that all earlier standards are taken care of as much as possible in the newer standard kind of thing. especially when ITU proposes something, it always tries to unify the existing standards the way they are available. So, some such effort went into the definition of SDH format again. This one is from ITU. Okay. It stands for Synchronous Digital Hierarchy. So, both are synchronous formats really. And as I was telling you, ITUT standards are used in most of the part of the world really, including the European countries, India and many other countries. So, now I will present a table, okay, where I will summarize the some basic parameters of Sonet and SDH, and we will see that SDH, which came somewhat later, has somewhat more general features, in a sense that Sonet can be considered now as some kind of subset of SDH. So, here is a table showing the Sonet SDH hierarchies, the some important parameters here. So, Sonet signaling formats I am presenting in the first column, then the corresponding Sonet capacity, okay, and the overall bit rate, and then the SDH signal formats and the corresponding SDH capacity. I have not noted the bit rate, you can calculate the bit rate, there is no bit stuffing etc. So, one can just directly by multiplication of the basic signal rate, one can find the ultimate time rate, bit rate. Pardon? Capacity means in terms of the basic signals, say here for example, in this last column when I say SDH capacity, I mean the capacity is being expressed in terms of say E1, E2, where E1 is the basic rate coming from the asynchronous hierarchy. So, a Sonet like STM0 is one kind of STM signal. STM0 will consist of 21 E1 channels, where each E1 channel, as we saw just now, means 2.048 megabits per second data. Okay. So, one STM0 signal comprises of 21 E1 channels. So, the capacity means we can now have an idea about the bit rate etc. How much, what is the transmission rate for STM0 signal? Is that okay?
All the units of this Sonet SDH are synchronous. There is no asynchronous.
No asynchronism in this. Okay. In fact, there was some intermediate technology, not was, even now it is in use, which somewhat a predecessor of SDH, which is known as PDH, Plesiochronous Digital Hierarchy. I am skipping that out really, but SDH is a fully synchronous digital multiplexing scheme. So, the abbreviations I have expanded here. STS stands for Synchronous Transfer Signal, the nomenclature given by ANSI while describing Sonet standard. OC stands for Optical Carrier, and STM, which is an SDH terminology, STM stands for Synchronous Transport Module. Now, let me read out these values and parameters column wise. First, the Sonet signals are known as STS1 or equivalently OC1 if an optical network is involved. Okay. So, STS1, then STS3, then STS12, STS48, STS192. These have been defined so far. Now, if the technology improves further, if the capacity of an optical carrier increases further, I mean it may be expanded later, but till now up to this much has been defined. Or correspondingly OC1, OC3, OC12, OC48, OC192. So, the point to be noted is that the corresponding STS value and the OC number, they are same always. Okay. I'll explain later. Okay. The capacity for Sonet has been expressed here in terms of ds. ds stands for digital signal. Okay, digital signal after multiplexing. This ds is something very close to, but not identical to, our T1, T2, T3 description. In fact, ds1 corresponds to very fairly to T1, the T1 description that we had. In fact, what has happened, as I mentioned briefly earlier, this T1 hierarchy, T1, T2, T3 hierarchy was originally from AT&T Bell Lab. Okay. Of late, this hierarchy has been modified a little bit. Some changes have been brought in the frame format, etc. And then this DS format has been suggested, and this DS format goes up to from DS0, which is our T0 kind of thing, 64 kilobits per second basic signal. Then DS1 corresponds very closely to T1 format. Then DS2 corresponds to T2, DS3 corresponds to T3, and interestingly, DS4 has not been defined, though T4 was defined. Again, T4 was defined from an earlier date, okay, keeping in view the corresponding existing systems really. But now, instead of DS4, the whole signal has been now taken up in the synchronous hierarchy, okay, so that Sonet takes over from DS3 onwards. There is no DS4 which has been defined. So, loosely speaking, DS1 means something very close to T1 format, multiplexing format, okay, though DS1 actually stands for the signal after multiplexing. So, STS1 or OC1 has the capability of transporting or carrying 28 DS1 or 4 into 7, that is 1 DS3 or T3, loosely speaking T3 kind of signal. STS3, it can carry 84 DS1 or 3 DS3 signals. STS12, it can carry 12 DS3 or 336 DS1. Okay, this is an equivalent expression I am noting here, but the format prefers, I mean, multiplexing 12 DS3 signals. The inputs will be in the DS3 form, and 12 of them will come, and that will be multiplexed to get an STS12 signal. STS40, I have just noted the equivalent DS1, multiplexing is through DS3. STS192, you can just see for the sake of comparison that STS192 is a huge multiplexed version, which equivalently takes 5376 DS1 signals, and the overall bit rate is close to how much? It's close to 10 gigabits per second. Okay. So, STS192 is a huge one. I mean, anything, there is no need at present really to think of a higher multiplexing format really. In fact, it is even difficult to achieve STS192. Okay. STS1, STS3, they have been achieved very easily, but it really needs very sophisticated technology to go beyond STS48 at the moment. For the bit rates are obvious really. The one interesting point is that because SDH came later, SDH formatted its, I mean, it's designed its format such that at some level of multiplexing in the hierarchy, it can also take up Sonet signal. This is a very important practical issue really. This SDH standard came later, okay, than Sonet. Now, when you devise a standard, it is expected that the standard will be used extensively, okay, and even if there are other non-standard other equipment or systems in place which follow different standards, if the new standard can accommodate those already existing standards, then the new standard can survive and serve the purpose better. So, it was felt that STH, because it is being proposed later, should at some point of time take even Sonet format signals, and it is at this level that it is ensured that as per the SDH hierarchy, the hierarchy was so defined, the rates were so adjusted that at STM1 level, the bit rate is the same as that of the Sonet signal. You please calculate this value and verify yourself. Okay. See, STS3 has a bit rate of 155.52 megabits per second, approximately 155 megabits per second. SDH also catches up with the Sonet data rate at this point. So, if you have an SDH standard in place in a system, and then if you have to carry Sonet signal, you will not be able to take the Sonet signal in STS1 format, because there the bit rate is different. Okay, your bit rate at STM0 is much different, much lower really. Whereas at if the data is available in STS3 format after from the Sonet system, then that data can be taken into the SDH format from that point onwards really. So you may have a situation where you may be carrying one STM1 signal as per SDH format, which basically may be a Sonet signal, or say one STM4 carrier, okay, which consists of, I mean, 4 STM1 signals really. Out of that 4 STM1 signal, one may be Sonet or 2 may be Sonet signals. This gives a lot of advantage really in terms of deployment of the system. Okay, so that's what has been ensured at this level. And then the SDH signals are STM0, STM1, STM4, 16 up to STM64, and the equivalent bit rate is quite comparable to this really. Okay, the values are a bit different. So now with this hierarchies, we can say that the multiplexing can be done at any level following these formats, one of the standards really, and one can get a multiplex bit rate starting from 64 kilobits per second to as high as a few gigabits per second, close to 10 gigabits per second. Is that okay? I do not expect you to remember each and everything, but please spend some time really to at least remember the basic or salient features of the Sonet and SDH hierarchies. Okay. So with that, I conclude my discussion on multiplexing and demultiplexing. Okay. Our next topic of discussion. Do you still have the general block diagram with you? I am not carrying it today, with me today. Please look back and tell me briefly what are the topics that you have covered so far. It's good to have a assessment of where we are, especially because the mid-sem exam is closing in. Broadly speaking, okay, let us discuss with reference to the general block diagram. Okay, the topics that we have covered. For example, what was my first block? No, before that, the source coder had blown up 2-segment one. Sampling, digitization, isn't it? Right, to get the information bearing sequence from analog or digital input really. Okay, so we discussed about what is known as, I'll now put it as is a form of source coding definitely. Okay, so I'll say AD conversion, PCM, etc. Okay, the overall purpose was digitization and recoding of analog signal, isn't it? Coding of analog signal. The sequence was different, but now we are following the sequence of the block diagram really. This portion we discussed later. Even before that, we talked about information theory, we talked about error control coding a little bit, then came to compaction coding of Huffman coding, etc. So now following this block diagram, so the first block we had some discussion on the first block. Then we had a block called source coder, where we, in addition to this digitization and coding process, we also talked about a compaction coding, or I mean lossless kind of coding, namely Huffman coding, is it not? With somewhat information theoretic approach. So both, I can say that conceptually both belong to source coding. What was the next block? We had some discussion, some preliminary discussion on that. Okay. What is the next block? Baseband processing unit, okay, and baseband processing and pulse shaping, okay, and in between one block was missing there, which I introduced later, is that of multiplexing, etc. That block diagram was a hypothetical one, considering a single user source and a single destination. Okay, if there are multiple users, then there is a need for multiplexing, and that's what we also discussed over there. So let me just note here with a circle that we also discussed about multiplexing. and the next block as per our nomenclature is baseband. I said it pulse shaping, isn't it? Let me say it is baseband signal processing unit. Okay, pulse shaping is a part of that. Let me rename it like that. So baseband signal processing. I want to highlight this term of signal, basically signal processing unit, which includes pulse shaping. Okay, because pulse is a kind of signal. We'll see the way the pulse is transmitted. Okay, now can we say that till the input of this baseband processing signal processing unit, okay, I can call the sequence of bits, okay, as some information bearing sequence. So I can talk about information just after my analog to digitization process, the moment signal is coded, isn't it? From that point onwards up to the input of this baseband signal processing unit, I can say that there is information from various users are being multiplexed, and the multiplex information now, if the signal has to be multiplexed, this is being fed to the baseband signal processing unit. Okay. Now from this baseband signal processing unit onwards, what is the next block? Just remind me briefly. Carrier modulator, if it has to be there. In our block we put it because our syllabus says we have to discuss extensively on carrier modulation, demodulation. Then we have a channel. Okay, what did I call that channel? What should we call that channel now? Now we had some discussion on the channel as well, various kinds of channels, is it not? Pardon? Modulation channel, that is the closest description. It's a modulation channel, isn't it? Okay, and the input to the modulation channel is going to be a continuous time signal after carrier modulation. Output from the modulation channel is going to be a continuous time signal, okay, which will be fed to the corresponding carrier demodulator and baseband signal processing unit, so that we get back some information which can then be fed to the error control decoder, etc., etc. Is it not? So now we will focus more on this baseband signal processing unit, okay, coupling the issue of carrier modulation in a smooth way. Okay, and as I said that our discussion in this course will be related mostly to narrowband signals. What do you mean by narrowband signal? The bandwidth is much smaller compared to the carrier frequency. Okay. Sorry. So let me take up the baseband signal processing unit. The earlier block of error control coder, source coder, one could call as baseband information processing unit. Those are also baseband processing units because no carrier has been used. Okay, the signal, the way it was there, the signal occupies similar bandwidth. It has not been transferred to a very high frequency carrier. Okay, so now I am talking about, I am focusing on the baseband signal processing unit. The input, I can say, is some information bearing, should I say signal? Sequence primarily. Okay, information bearing sequence, and we know it is random. I mean, it is expected that it will be random. Okay, so that's the expected input, and the output from this signal processing unit, which has to go to the carrier modulator. Okay, what should this be? I can say the output is some kind of signal. Okay, signal first, at the first level, this is some signal. Now information bearing sequence has to be represented somehow, is it not? I know you are very familiar with, if I ask you to draw a random information sequence, you will write a binary pulse train kind of thing. Okay, this kind of sequence. And if I ask you, is it a signal or an information bearing sequence? Please note that for representing an information bearing sequence, one may not talk about signal, is it not? You could simply write it as 1011 kind of sequence. So far as the information is concerned, that would be reflected by the same manner. But from now onwards, because we have a task of transmitting signal from one place to the other one and receiving and retrieving the information from there, from this point onwards, we have to talk about signal, which means there is a very subtle need of representing this information bearing sequence in appropriate signal form. I say it is subtle because this is some issue. If we do it nicely, our purpose will be served very well. You have a hint of this already, because what you have found already in your tutorial course is a kind of spectrum which is occupied by this kind of random sequence, and you have seen that the spectrum, when the sequence is random and when it is represented by two sharp pulse values of say 0 volt and 5 volt, just considering TTL1, I mean it stretches to a very large bandwidth, is it not? So if I try to represent my information bearing sequence by this kind of 2 voltage level sharp pulses, then the bandwidth of the signal at this output itself is going to be very large. And if the bandwidth that I am going to use as my modulating signal to the carrier modulator, if the bandwidth of that itself is too large, then I cannot achieve narrow band carrier modulation scheme. Okay? Not only so, there is another important issue. The issue is not only to transmit over a narrow bandwidth, the issue is, which is more important ultimately, is to be able to detect and get back this sequence or this information bearing sequence somewhere in the receiver. Okay? So this issue of representing information in appropriate signal format is very important for a communication system designer. Okay, we will focus more on that really. Now, just one basic question: even if my information bearing sequence here is a binary sequence, let me say 1 0 1 1 0 0 1 etc., is it necessary that I have to generate a signal corresponding to only two possible values here, or in this processing unit for some reason I can also think of some group, say group of 2 bits or group of 3 bits etc. Would you allow that in a very general form? Yes, why not? The information may be available in a binary sequence, okay, but it is not necessary, it is, I mean, it's not mandatory to generate only two kind of signal at the output. Is that okay? I mean, for convenience, for some subtle reason, for some reason, we are free to group them here. Okay. Now, sorry, we are also assuming one thing right from the beginning, is that whatever is the representation, basic representation, if this is the actual representation of the information bearing sequence at the input, which is a 2 level binary signal, this is a signal now in terms represented in terms of voltage. Okay, if this is so, we are assuming that this has got 2 levels. That means for 1 bit I have this pulse, okay, and this pulse has a duration. Let me say that this duration is TB, bit duration. Okay, then the duration for the next bit, which here is 0, say, is the same. So each bit has got same duration. That's what we have been assuming. One can contest, why, sir? Okay, in general it need not be, but for most of the cases it is like this, for the sake of simplicity in the design of signals, in the transmission of signals really. Okay, though there are schemes available. So what we can now assume is that TB is something constant, is a duration of one information bit I am writing. Okay, so I am framing a base for my discussion for next few lectures really. So we will assume from now onwards that TB is the duration of one information bit. Now, if I consider grouping of, say, small m number of bits together, okay, and call this group of small m bits as one symbol. The moment I talk about grouping, really I am grouping small m bits, number of bits. Small m may be 1, that means one bit is one symbol, or small m may be 2, 3, etc., some integer, small integer. Then this group of small m bits I have to name, and I will call that as one symbol. So let one symbol be a group of small m bits. Okay. So how many symbols are possible at this input? 2 to the power m, is it not? Only 2 bits, 2 different kinds of bits were available earlier in the binary form. Okay. So I am considering group of m bits together. I am calling this group of m bits as one symbol. So number of different symbols is only 2 to the power m. Here again, as an example, we are considering a binary sequence right from the beginning, really, but that also can be relaxed. One can talk about a non-binary sequence and then grouping of them, etc. It's a more general thing. We need not worry much. So the number of different symbols is 2 to the power m. Okay, and what is the symbol duration? Can I define some T of S? Yeah, symbol duration is MTB. Okay, let me have a name for this discussion. Let me call broadly that this discussion is related to signal design. Okay, signal design. Initially we talk about baseband signal design, subsequently we will talk about modulated signals. Okay, after we talk about modulation, carrier modulation. So let this be, the topic be signal design, starting with baseband signal design. Okay, so I can consider group of m bits to define a symbol, and the symbol duration will be Ts, which is m times Tb. Okay, and the number of such symbols is 2 to the power m. What we find is that there will be only a finite number of symbols available at the input of this baseband signal processing unit. Okay, depending on value of m. Okay, maybe 2, 4, 8, 16, whatever it is. It's a finite number. Okay, then what do I generate what do I generate at the output? A fundamental issue is that I can say that at the input, as if there will be one of the possible 2 to the power m symbols available at a given point of time, and the symbol will exist over a time of m times Tb. After that, another symbol will appear. Is it not? Okay. Then how is this idea that we generate one kind of pulse for each kind of signal, because each symbol is of duration mTb. Okay, so why not I design 2 to the power m different pulse, okay, and I'll represent each symbol by one pulse, which is time limited. So the issue is that we have 2 to the power m symbols at the input, and what we generate at the output of this signal processing unit is 2 to the power m time limited pulses. 2 to the power, each symbol has got a duration of Ts. So what I'll give out is a pulse of duration Ts for every symbol. Each symbol will have a different looking pulse. We have to find out what should be the relationship in the pulse shape, etc., etc. But the first thing what we can agree is that for each symbol we will have a specific pulse. Okay, one kind of pulse which will also exist during this Ts time. So by this I am not violating anything. I am not talking about mixing one pulse with another one. So as the symbol changes at the input, the corresponding pulse also will change. Okay. So, if I have a sequence say 1 0 1 1, and if we have decided to group 2 bits at a time, so there are 4 possible pulses, then for this 0 1 combination I may like to design some pulse say like this, whose duration will be how much? Ts, which is 2 TB, is it not? Okay. And when this pulse changes to another pulse, say another symbol of 1 1, I have to design another pulse for that, is it not? The pulse shape, just for the sake of very arbitrarily, let me say the pulse shape is something like this or even different looking one, but the point is that the duration is the same Ts, so that we are not talking about mixing one pulse with another one. Okay. If I do only this, then looking at this pulse trend, can I get back my information? Huh? This is very important. So, what shall I do in the receiver? At the receiver, I will try to observe what kind of pulse I am getting over an interval of Ts, okay, and then try to find what is this pulse. Is this pulse anything defined in my alphabet? There will be some uncertainty, because during transmission there will be some other kind of distortion and noise, etc. So, even if, for example, for this group of first 2 bits, if I transmit this pulse of duration Ts, I hardly expect to get it so clean at the receiver, isn't it? There will be some distortion. Okay. Now, one common form of distortion is that through noise, okay, so that it will require somewhat look somewhat different. It will be noisy over there. But then my approach will be, from whatever I receive over a duration of Ts, I will try to find the closest match of what I have received with the defined possible pulses. There are 2 to the power m possible pulses. I will find and try to find the match, closest match of what I have received with whatever were possible. Okay. So, that again will be my heuristically my reception or demodulation strategy. So that if I can identify that, okay, this pulse, this is the pulse which is closest to the pulse corresponding to this bit, so I clearly give out 0 1 as the corresponding bit out, and my demodulation is over, is it not? So, intuitively it is like that. Of course, you may raise a question that, okay sir, the channel may distort the signal such that though the pulse was transmitted only within this interval of Ts, okay, while you are receiving it somewhere in the demodulator, this pulse may spread even, while it may get distorted, it may even spread beyond this boundary, this limit of Ts, okay, that may happen, and we also gave a name to that kind of distortion, if you remember. Yeah, yeah, usually this kind of situation should not occur if the modulation channel bandwidth is greater than the bandwidth of your modulated signal, okay, if the channel is time invariant and if your channel is linear. Did you talk about this? Linear time invariant channel. I did talk about time varying channel and time invariant channel briefly. Well, so for our discussion, we will assume that our channel is time invariant. The basic nature of the channel does not change with time really, okay, and the channel bandwidth is or should be sufficient for transmitting the modulated signal. If the channel bandwidth because of some reason is smaller, then that may lead to this kind of distortion. Okay. If the channel is not linear, if the channel includes, your modulation channel does include some kind of amplifier, power amplifier. If you think about the modulation channel, the modulation channel consists of the propagation channel or the radio channel and the front ends, transmit amplifier, receive amplifier, etc. Now, if the transmitting power amplifier does not have any nonlinearity problem, okay, the gain output input characteristics is linear, then there is no reason why it should spill over really. If there is a nonlinear amplifier, then the pulse may get distorted. So there may be multiple reasons why the pulse may not get restricted here. Okay, it may spill over. The energy of this pulse may spill over to the subsequent one. Okay, we will assume that there is no such thing. For basic fundamental understanding, we will assume that the channel is a nicely behaved channel. Its property does not vary. Property means statistical property. Okay, does not change with time. Okay, so it's time invariant, and the channel, this modulation channel, is linear. Okay, so that there is no additional distortion by the modulation channel. In that case, there is no reason, if my transmitted pulse is limited to this duration Ts, the received pulse also will be limited to Ts. Okay. Now, before I stop here today, tell me that this pulse, the way I defined, okay, there are 2 to the power m different pulses. We will see how to come out with such 2 to the power m different pulses and what kind of property should be there. That is the topic of our studies subsequently. But a very fundamental thing is that this pulse, the way I am trying to look at it, is ultimately a time limited signal. Can I say it is an energy signal? Is it not? Okay, it is not a power signal. Fine. So, this pulse that I am talking about is a time limited pulse, okay, 2 to the power m in variety, okay, and they are energy pulses, energy signals. Okay. It is obvious. I mean, if I choose, for example, say, if I choose this to be one pulse or one symbol, and if I choose this to be another pulse for one symbol, okay, if it is justified, okay, then one can just by looking at these two steps, one can say that, well, the pulses are similar looking, but the second pulse has got much smaller energy. Okay. Now, when our problem is to give a mapping for each of these 2 to the power m symbol to one of the 2 to the power m pulses, would you like to assign a pulse with smaller energy to one symbol and a pulse with larger energy to another symbol? Would you like to do that? Yes. Tell me what is the reason. Is my question understood? When the problem is to assign one pulse to one of these 2 to the power m symbols, then would you like to assign a high energy pulse to one symbol and low energy pulse to another symbol?
Most probable things can be assigned low energy pulses. So the total power
Most probable pulses should be assigned low energy. Why? What is the basis? You are trying
the transmitted power should be less.
so that the average power is less. Okay, that's the reason, is it? But my point is this. See, this is the input to the baseband processing unit. We have done all kind of. We have exploited the probability difference of the input symbols or letters in the alphabet already in source coding or channel coding or somewhere else really. So, is it not that all the symbols are equally likely at this input? Why should there be a bias or difference in probability for these symbols? Why? Think a little bit. My point is that, see, at this input to this baseband signal processing unit, the symbols are of equal probability. One should not look for a probability range of all these symbols, because if it was there so much, it should have been exploited earlier through source coding, through Huffman coding, or by other means, by your DPCM and other schemes. So, at this point, it is a very fair assumption that all symbols are equally likely. We assume that, and that is a very fair assumption. No, all symbols are equally likely. Think a little bit. There is no reason why there should be a lot of probability difference between 0, 1 and 1, 1. Okay, because fundamentally each bit, even in the binary form, the way it was available, the sequence was available, the probability of 1 and 0 was same. I mean 0.5. So, in symbols also there was no difference in probability really. So, all symbols are equally likely. Yes.
So when we have done source coding and channel coding, suppose
Right.
we did Huffman coding,
Right.
so you have a variable length code, or suppose you do the source coding either systematic or systematic, you have those first k bits and then the end.
The parity bits.
Parity bits at the end.
Right.
Now once you are coming here and now you start picking a group of bits, so won't they be split up? So if you have variable length coming,
Right.
and you used to pick up every 2. Now that one symbol which was coming says least probable 1 1 1 0 something like that. Now that has been split up into 2 or 3 or.
No, you have got multiple questions really. One is that, I mean, in this grouping, is it going to disturb the previous coding format, whether it's a variable length, fixed length? My point is that no, because at the output of your baseband processing unit in the receiver, I'll give you back this binary sequence the way I received it. So when you follow your regrouping operation at the source decoder output, you should not have any problem. Okay. Well, let me just raise the question before I stop here today. It's time really. So no, here we can assume that in fact certain other operations are carried out to ensure that the probabilities of symbols are same really. We do what is known as some kind of scrambling operation. Okay, a definite randomization operation really. So that at this point all symbols are equally likely. If it is so, then do you see that all symbols, do you feel that okay, some symbols should have lower energy, some symbols should have higher energy? Usually not, usually not. Okay. So we will try to assign same energy to all the symbols. Okay. And we will follow further in the next class. We will discuss what is known as Gram-Schmidt orthogonalization, but that is after the mid-sim. Thank you.